we begin. Today's speaker is Hilde Nesse, and she's a team leader of one of the 3 research groups at the Bergen Center for Space Science at the University of Bergen in Norway. And the group is addressing the effects of particle precipitation on the atmospheric system. And it currently has 12 members working together in a cross-disciplinary field bridging the gap between space physics and atmosphere science. And this fall she's visiting NCAR, mostly at ACOM, and also the University of Colorado on a Fulbright fellowship. And she will talk today on the energetic electron precipitation into the Earth's atmosphere.
Thank you. So I will discuss to what extent we are able to quantify what is hitting our atmosphere, and also some of the challenges associated with it. But before I start, I will address the motivation behind doing this. So particle precipitation can hit our atmosphere coming directly from the solar wind through these rare solar proton events, and then they will deposit their energy all over the polar cap. But typically, more frequently, the particles is hitting the atmosphere coming from our magnetosphere, either from the plasma sheet, where we have the auroral precipitation, or the trapped population, the radiation belt particles, from a little bit closer to the Earth. And I will point out that the trapped particle population, that is one of the outstanding questions in terms of quantifying what is hitting our atmosphere. But regardless for where they come from, particle precipitation increases the ionization, which initiate a series of chemical reactions, which increases the production of NOx and HOX gases. HOX basically lives and breathes with the ionization, it's short-lived, while NOx will have lifetime of months as long as it's not exposed to sunlight, which means that during polar winter you will get an accumulated effect of all the NOx production throughout the winter. It's a difference with the different sources. Its auroral precipitation is typically associated with electrons less than 30 keV and will deposit their energy in the lower thermosphere, while the trapped population coming from the radiation belt can have quite high energies, larger than 30 keV to relativistic, and will deposit their energy throughout the mesosphere and the upper stratosphere. The long lifetime will add all the events over the winter, more or less. But in addition, the background dynamic preserve the anode being produced within the polar vortex to high latitudes, and so it doesn't get exposed to sunlight at low latitudes. In addition, the background dynamics will push it further down into the atmosphere, and when it reaches the stratosphere, NOx can efficiently destroy ozone in catalytic reactions. Ozone is important for the energy budget in this region. It doesn't necessarily impact the main ozone layer, which protects us from the UV, but in general, since ozone is important for the energy budget, it will be changing ozone will then change the temperature, and if you change the temperature, you will change the wind and possibly how wave is being refracted. And it's speculated, which indicates the dashed box here, that the winds up in the upper stratosphere might have links all the way to our weather system. But to do a good job in estimating the total EEP, the particle precipitation effect, we need to do a good job with the first step, estimating the energy that is being deposited into the atmosphere. And although I say it's speculated that there is a link that can be all the way to the surface, the physical mechanism has been kind of approved for in the sense that it's particle precipitation is no part of the coupled model intercomparison project, which is which we call the CMIP. That means that in this coupled model intercomparison project, there is a parameterization for energetic electron precipitation. It's basically a model of the precipitation parameterized by AP, the geomagnetic index AP, and it will be used extensively in different types of model, and it's no part of WACM 6, the standard input. So the first part of this talk will focus on we'll compare the AP model parameterization to a different estimate, which we call the loss cone fluxes, which is estimated by our group, and compare to what extent the AP model and the EP fluxes are in terms of overall flux strength, but also if there is some systematic differences when it comes to the energetic EP driver. If it's if it looks different, if the fluxes look different when you have a solar wind driver, which is a coronal mass ejection, or when you have high-speed solar wind and co-rotating interaction region-driven storms. And as part 2 of this talk indicate, there is some challenges associated in particular with the CIR storms, which I will address. But first, let's talk a little bit about this AP model that is recommended into this coupled model intercomparison project, and how it looks like basically. So it is based on, it models electrons from 30 keV to 1 MeV. It is based on the polar orbiting satellite POES and the particle detector MEPID, the 0-degree detector. So basically the model is built up as a function of ALSHAL and AP. So all the data from the POES is basically sorted into bins, and finally there is a mathematical description trying to resemble how the data looked like. But the authors themselves, details of this you can find in Van der Kamp et al. 2016. But the authors themselves, they say that due to limitation in the first version of the model, the results most likely represent underestimation of the total energetic electron precipitation effects. So what do they mean by that? Because as this model is being used in so many model runs to estimate the EP effects, we need to understand what this underestimation is. Well, it's due to limitation of the data. It uses the MEPID instrument, which consists of 2 electron detectors and 2 proton detectors, which is pointing vertically and horizontally to the polar orbit. At high latitude, the 0-degree detector looks almost along the magnetic field line, which implies that it looks within the loss cone. Loss cone is the outer boundary of all the angles that is small enough to be they will be precipitated, lose their energy into the atmosphere. So in this case, here is one example of how the geometry could look like, where the light shaded gray is the loss cone. The 0-degree detector is here and the 90-degree detector is here. But where they are pointing will vary with this satellite orbit. And this is kind of a best case scenario where the 90-degree detector sees partly within and partly outside the loss cone. In the case, and one advantage with a polar orbiting satellite, POIS is around 800 to 850 kilometers, and that means that the loss cone is fairly large, between 50 and 60 degrees, which enables a detector to see within it. So that makes the polar orbiting satellites kind of valuable in that sense. So here is an example of the size of the loss cone, which is here about 58 degrees. This is flux on the y-axis, and you have pitch angle on the x-axis. So it's a distribution of fluxes as function of pitch angle. And here is the red loss cone and the flux we wish to measure. In this case, when you have a fairly isotropic, almost the same number of particles at all pitch angles, then it wouldn't matter if we use the 0 or the 90-degree detector. It will basically measure the same level of fluxes either way. But this is not the typical picture, because the problem arises when the electron flux is anisotropic, which it typically is, especially for the higher energy electrons. So then we wish to measure this level while the 0-degree detector sees too little and the 90-degree detector sees too much. And this is a logarithmic scale, which implies that the 0 and 90-degree detector often are measuring fluxes that is 2 order of magnitude difference. And the loss cone value is somewhere in between. So when the AP model only uses the 0-degree detector, it means that it underestimates on basically all the time. It could be have the right, if it's isotropic, it have the right level, but typically in the anisotropic case, it gives an underestimation of the electrons hitting our atmosphere. In Bergen, we also use the POIS and the MIPID. We have done a lot of correction and optimization of the data. So we have new optimized energy limits and geometric factors, which you can see here. More details is found in this paper. We use proton measurements corrected for degradation to account for proton contamination in the electron measurements. And contamination is not always bad, because electrons will also hit the proton detector. And if there is no protons in P4 or P5, we know that the P6 channel measure relativistic electrons, so we basically add an extra energy channel. And we deal with the anisotropic fluxes by using both the 0 and 90-degree detector. Together, we're taking into account the detector response for different pitch angle directions and fit the fluxes measured by 90 and 0-degree detector onto the Fokker-Planck equation. And then we use the distribution to estimate what is the total flux within the loss cone. So in comparison to the AP model, we take advantage of the information that you have in both detectors. So in the comparison that will follow now, I will look for the differences in the overall flux strength using what I call the loss cone fluxes and this AP model. And I will look at how it changes with time, if there is a difference throughout the solar cycle and associated with the CIR and CME events. And finally, I will question whether or not we are in the right region in terms of being able to estimate what has been going on in the future in the right time period. So here is the overall flux strength. We have Alshal on the y-axis, AP on the x-axis. So here is the mathematical description, which is the AP model. So we can have that for different energies, it's just the equation. As expected, since this is the loss cone fluxes that uses both 0 and 90, and this is based on just a 0-degree detector, we see that we have about an order of magnitude general difference. The features are more or less the same in both pictures, and we have forgot to mention that we sorted the loss cone data in the same manner as they did to make the AP model, so it should be comparable. But yeah, general or more, both an order of magnitude more in the loss cone data compared to the AP model, but the feature is more or less the same except when you go to higher energy. Then the AP model gives you a kind of local maximum here in the heart of the radiation belt. Maybe if we follow an L shell to higher AP values, like this line shows, then we kind of have a local maximum at quite low AP values, which we don't find in the loss cone data. So whether that is physical or not could be discussed. But as expected, more fluxes in the loss cone data. So the question is then, how does this vary with time? Because throughout the solar cycle, we basically have two main features that will drive particle precipitation events. You have the coronal mass ejection driven storm, which gives a general strong geomagnetic index signature, here shown in DSD. And most of the particles is typically coming in the main phase of the storm, also some in recovery. But for the CIR storm, they are typically relatively weak because they are associated with an oscillating magnetic field, so they don't necessarily give a very strong geomagnetic signature, but a relatively weak one and a long-lasting one. And the literatures say that a lot of the particles, the electrons, especially the relativistic one, is coming in the recovery phase of the storm, when the geomagnetic signature is quite weak. So how is that? So that intuitively makes it a little bit difficult to estimate the particles based on a geomagnetic index. And they're not equally distributed throughout the solar cycle. We know that the CME are associated with sunspot, which makes it follow the sunspot number to a closer degree. Here the red is sunspot number and the black is the AP. So the CME will follow the sunspot number, but we see that the AP has an offset of 2 to 3 years, which relates to that it responds to a combination of CME and CR. And in the declining phase and in the minimum phase of the solar cycle, these coronal holes can penetrate down to equatorial latitudes on the sun, so it's their associated high-speed solar wind streams points towards Earth. So we will have more of them in the declining and minimum phase of the solar cycle. So the next question is then, how will that give a bias throughout the solar cycle in the AP model compared to then when we're using the measurements, the estimates based on the loss cone fluxes. So we selected a few years throughout the solar cycle we're looking at. We're looking at 2003, 2005, and 2008. The most striking difference is that you don't have fluxes for high AP values during solar minimum, because it's solar minimum. But generally, it's not a very striking difference between these, looking at the full year. But in terms of the low L shells, there is some difference, which makes sense because in 2008 was basically just CIR events, and you don't get these, auroral oval expansion associated with it. So it kind of makes sense that differences to be see here. But what we notice in terms of when you take daily values and look at the total amount of fluxes throughout the years, we see that in 2003 the AP model captured about 30% of the fluxes that we estimated from the loss based on the loss cone method. While in 2008 it captured 10%. This means that the AP model might exaggerate the difference between solar max and solar min. So even if it's an underestimation, it's less of an underestimation in the high activity year compared to the low activity year, which we could keep in mind. Here is a full year, 2003, and it's a little bit, it's not, yeah, I will explain each panel. The lower panel, you have days, day of year, on the y-axis, and you have the AP value here in the lower panel on the y-axis. X-axis Tyssoy, and y-axis AP. And here we see the famous Halloween event, which was quite strong. These are the panels showing flux, estimated daily averages flux level for different L values, which correspond to about 61, 64, and 69 degrees. Here is the L value. And the black line shows the AP model. The two colored lines are the loss cone fluxes, but there are two of them, because these are data, and we have bad data, because we have a lot of restriction on it, and so we to be careful and just use what we think is correct. So we throw away some data and call it not a number. That's one alternative to deal with bad data. Often these bad data occurs when you have very low fluxes. So you could also put them to 0. But either way, if you treat them as not a number, or if you treat them as a 0 value, you will get a bias in the data. So this is to show you the bias that we have. But very often they show more or less the same, like in this case. And then we're pretty sure that we have a lot of good data, and they are consistent. So let's focus a little bit on the Halloween period, since that's so famous. And then we notice something with the AP model that we don't see in the loss cone fluxes, is that it kind of reaches a plateau. And if we look at the description or kind of plot of how the fluxes depend on AP, like here, for the same L shells. So if we then focus on here in the middle, which would correspond to this red dashed line, we see that explanation for this plateau. So around 30 AP, it will reach a kind of maximum value. It just slowly increases after that. That means that all the times, all the days that have an AP value of about 30 AP or more, you kind of reach the maximum fluxes that this AP model will give. I've also done the same exercise for the loss cone fluxes, and then from 30, I don't show it here, but then from 30 AP to about 80 AP, it increases by an order of magnitude. It flattens, but it's still an increase. So it's so they disagree in terms of how the fluxes behave as a function of AP. But we should be aware that it is a maximum value, and it is representative for all L shells, so it basically reaches a maximum value of about 40 AP. So everything above will give you the same fluxes when you use it in a model. But that also means that there will be large variability associated with the low AP values. And that is kind of illustrated looking at the CIR events. Here we have the AP in the lower, this red dotted line, and the AP model is here in black. And we see how nicely it rises together with the AP in the beginning of the storm, and right in the beginning of the storm they don't necessarily disagree that much with the lost cone flux. But in the recovery phase of the storm, the AP model drops as the AP drops. But the lost cone fluxes still says there is a lot of particles coming in. And we have done the exercise of saying that, okay, let's estimate how long this CIR storm lasts by saying that when does it drop to half its maximum value. And in this case, using the lost cone, we would get a storm that lasts 4 days longer compared to the AP model. Looking at all storms in 2008, the lost cone, the storms based on lost cone fluxes last 50% longer than the storms based on the AP model, and in 2005, 35% longer. We couldn't use the 2003 because we need isolated events to find out the length of our storms, and in 2003 there is a new one coming all the time, so it's hard to isolate them. But that kind of points out that I think, looking at this, there is an issue in trying to model CIR storms based on a geomagnetic index, as a lot of the particles will come in the recovery phase of the storm. But the fact that the AP model is quite sensitive when you have low AP values actually it gives it a better correlation with the lost cone fluxes in 2008. And in 2008 we had the largest underestimation compared to the lost cone fluxes. But the correlation just tells us about the variability, and in that sense it does a better job in 2008 compared to 2003. But it's still a quite good correlation in terms of variability. And finally, in this comparison, I will address this saturation effect a little bit more, because the model is based on the years from 2002 to 2012. And we look at the solar cycle here in dashed black. This period is not necessarily representative for a strong solar cycle. The blue circles here indicate the number of days during the different years you reach the saturation level, you reach AP above 40. And it's not that many days, although we saw that they saw the effect in the data as a plateau, but it's still not that many days, because when we go back to previous solar cycle, we can reach as more than 40 days where you get the saturation effect. So this is a problem when you go using this input and try to estimate the EPP effect going several solar cycles back, and then we should be aware of that there might be a larger underestimation than I've shown so far because of the saturation effect. But this is a problem that if we try to make a model by our own based on the lost cone fluxes, we will still have this problem, because the good data, when you have multiple satellites, is in this fairly quiet period. So the next solar cycle would not be more helpful. We might not be able to see the maximum flux level that could be dumped into the atmosphere based on the modern, this century time period. So this is not just a problem for the AP model, but for future models as well. I will not let go of this CIR storm yet, because since I kind of already concluded that it's hard to model them by geomagnetic indices. The question then pops up, how should we model the particle precipitation associated with it? Is there some parameter in the solar wind measurement that would be helpful? Or maybe we need to look at the geomagnetic indices in a context, kind of to identify what kind of solar wind driver we have to begin with to be able to model the fluxes. And if we're going to do that, we also need to understand a little bit of the nature of energetic electron precipitation during these types of events. So I'm continuing now just looking at the loss cone data. I'm using a superposed epoch analysis based on isolated event from 2006 to 2010. It's we will find 41 weak to moderate isolated CIR storms, and as you see here, they're quite weak because here is DSD minus 50, and some of these storms wouldn't even qualify as a geomagnetic storm in the usual, using the usual criteria. But we see that we have selected them as it's purely a CIR storm or high-speed solar wind-driven storms, as shown here. And it's interesting to see how much is coming down in this period where we have quite weak geomagnetic signatures. The zero epoch is based on the pressure, when you have a maximum pressure increase here. And we should note that the magnetic field does not necessarily behave as nicely as we often see during a CME event. It doesn't become negative very clearly. It basically oscillates with a quite high frequency. So it kind of the envelope here shows that in this period when the high speed, the solar wind speed increases, then we get a fairly, an oscillating magnetic field. As many have done before us, we sort these into how the fluxes compares to pre-storm level. Because one of the challenges that the radiation belt community has asked themselves is that, we see that it's coming a CIR storm, and sometimes you get an increase in the radiation belt, sometimes you get a decrease, or maybe not a change at all. And how would that then look in the particle precipitation? So we use the same kind of sorting as they do in the radiation belt, but different from the radiation belt study is that this grouping is made on the loss cone fluxes. We're looking at what's being precipitated. Group 1 is the storms that gives more than a doubling of the larger than 750 kV fluxes 2 days after the zero epoch. So we compare post-storm fluxes to pre-storm fluxes. In the group 2, the storm do not show this signature, but if we go look at a lower energy channel, larger than 300, we still see an increase. In the last group, we don't see an increase in the larger than 300, and if we look at the super epoch here in larger than 750, we actually have a decrease. It's kind of hard to compare a picture, so we do the average from 55 to 70 and plot them as lines here. So here we have the same groups. Then we have the blue one, which gives you the increase in the larger than 750. And group 2 is now the green one here, where we had the increase compared to pre-storm level in larger than 300. And the pink one, we get no change or decrease. But what's interesting when we plot them up as lines is that, some features kind of stand out. Group 1 definitely has more seed particles. And by seed particles, I mean lower energy particles, because these high energy particles start out as 30 keV and then being accelerated to 100 to 300 and then 750. So to get particles here, we need to have seed particles, lower energy particles. So group 1 definitely have more seed particles. Group 3 have higher pre-storm fluxes compared to any of the other groups. But the most interesting feature, I think, is that although we sorted group 2, we put group 2 and 3 in, separated them based on the how they related to the post-storm fluxes. They both show the same level afterwards. So it's not necessarily that you have a, maybe it's not the reason that you get a group 3 is because they had a higher pre-storm flux. I will come back to that. Here is some selection of solar wind features and geomagnetic indices. Group 1, which showed the increase, shows the strongest solar wind, and group 3, which had a decrease, has the weakest solar wind, or it lasts shorter. But in general, I don't think this trying to correlate that with the fluxes afterwards is not evident that it's directly related to the solar wind. BC seemed to be a much more likely candidate. Remember that BC is oscillating, but it matters where the oscillation occurs. So in group 1, this negative signature here shows that it oscillates around a negative BC value. That means that more energy is coupled into the magnetosphere during the group 1 storms. Well, it's not easy to separate the group 2 and 3 storms in this case. But group 1, having a more negative BC, means more energy, here shown in terms of epsilon. Shows that there is more energy, storm time energy, available in the group 1 storms. More storm time energy, stronger geomagnetic signatures as well. And we looked at a lot of different parameters, including the indices, and tried to correlate, tried to predict based on the indices which gave you the strong particle precipitation. But there is not clear. It was not easy. We used a different combination of it as well. But the most promising candidate is actually this the epsilon, and I will show it here. Because the energy that is being deposited into is coupled into the magnetosphere has its maximum around just after 0 epoch. But we look at the fluxes. They basically don't reach a maximum until several days after. So it's not correlated in time, it's a delay here. In fact, we said that, okay, let's accumulate the available storm time energy from 0 epoch and see how that correlates to the fluxes that's being precipitated into the atmosphere later on. So here is the storm time energy from the different groups accumulated over time. It's not evident how long the accumulation period should be, but just an experiment. And here are the fluxes. They're shown before, larger than 300, larger than 750. Larger than 300 is the black line, and here shows the correlation as function of time. And we see that at about 2 days, it seemed to be fairly well correlated. And then we don't use the group as a group. We have the 41 individual storms in this correlation. And it seemed to, at about 2 days, we get a fairly good correlation. And another thing is that the different storms, the 41 storms, seem to behave in the same manner in respect to the available storm time energy. for both larger than 300 and larger than 750 kV. It's a bit more scattered here, but there's a clear tendency with a good correlation. And one important thing is that even though we sorted them into different storm groups, they doesn't behave as fundamentally different. They have the same dependence. In fact, you see here that the group 2 and group 3 storms basically have the same available storm time energy, and they have the same level of fluxes after the storm, regardless if they started out with quite different storm time fluxes. And this might point to a possibility that epsilon could be used as an estimate to estimate how much particles is being precipitated. But let's look a little bit more on these fluxes at different energies. I started talking about pitch angle and isotropy. And how does that behave? What is the pitch angle and isotropy during these types of events? So here I choose, you can, I think it's cutting off, not on my slide, but this is the ratio between the 0 and 90 degrees. So with using the fluxes more directly, not through this loss cone estimate, but the 0 and 90 degree fluxes, and here is the level of fluxes in the 90 degree detector. So in that sense, we can use the 90 degree detector as so that will be more representative for the trapped fluxes. So this will be more representative for how the radiation belt will grow or behave. Well, this saying which kind of the fraction that is being deposited into the atmosphere. So for larger than 40 kV here, it seems to be a tendency that the higher the fluxes in the radiation belt gas, the more it's also being deposited into the atmosphere. It's a bit of a mix when you get into larger than 100 kV. It's not as clear, but looking at larger than 300 kV, it seems that as the stronger the radiation belt, the 90 degree fluxes become, the less is being deposited into the atmosphere, the stronger the pitch angle and isotropy is. So I would say that the level of diffusion or isotropy and isotropy depend on the flux level. It doesn't seem like, if you kind of see the different storm groups also behave fairly much the same here. So it seems like it's more the level of flux that decides how, not necessarily decide, but it corresponds to a certain anisotropy. This implies that basically this CIR storm will, even though the radiation belt grows, it will deposit very little of these particles into the atmosphere. But if we're thinking of how we use the 0 degree detector, if we only use the 0 degree detector, you will still get a large underestimation, because with the stronger the anisotropy, the less of the fraction, the less representative it becomes for the loss cone. So it's kind of a double edge. It seems like the CRR storm in general is not that efficient in giving us energetic electron precipitation, even though the radiation belt grows here at relativistic energies. As a smaller fraction is being deposited, but still, if we only use the 0 degree detector as the AP model is based on, then we see relatively less of the loss cone and what is being deposited into the loss cone. So larger underestimate in this recovery phase, because these higher fluxes here corresponds to the recovery phase. The higher fluxes here means that we are fairly well into the recovery phase. We looked at different local times, and they basically look like this, except in the evening sector. Then it's becoming much more scattered, which we can understand based on the emic waves, which we know is pushing the electrons to smaller pitch angles and into the lost and atmosphere. But the fact that they kind of behave so nicely, I would say, in terms of increasing flux level, could indicate that we're basically looking at the same acceleration process, but group 1, as I mentioned in the beginning, had a different seed population. So if you kind of have the same acceleration process, but more particle to accelerate, you will also get more fluxes later on. So this kind of gives us an idea of the nature of the energetic electron precipitation during these CR storms, and gives you a hint maybe of how we can parameterize them better. But still, it's not easy. So in summary, is these two focusing on these two topics, I would say that we have if you're using the AP model, you will underestimate the effects on the atmosphere. In particular during the CR storm period. And to address the CR storm challenge, we see that this could be explained partly by that we get larger pitch angle anisotropy associated with larger fluxes. But we also see that it correlates well with the available storm time energy during the period. But to do a better job here, I would say that we need to get better measurements. And I'm fairly optimistic because there is there's several small satellites with the particle instrument that aiming to measure the pitch angle. Because if we have if we know how the pitch angle varies, if the distribution varies, then we can estimate the loss fluxes fairly well. So I know there is one flying now that has a spin to measure the fluxes at different pitch angles, and there is several other initiatives with different techniques. And I also think the fact that we see, now that the Vanallum probes area has kind of come to an end, maybe we can get some of the expertise in the radiation belt also into what's being into the EEP, because I think they have a lot to contribute in terms of understanding the nature of these particle precipitation, what's being lost. So when it gets to future measurements, in Bergen we also have designed a particle instrument, an electron detector that will measure from 30 to 500 kV. It has two silicon detectors on top of each other, and it's pixelated. So we should be able, in theory at least, to get a fairly good pitch angle distribution. And the intent is that there should be 3 of these detectors. So in total, it will cover a pitch angle region of about 180 degrees. So there will be 3 of them. And we come to the point that it has materialized. And we have one of these detectors mounted on a rocket that will launch at the end of the month. So we'll do a technical test and see how it behaves. So maybe in the future it will come an opportunity to fly it on a small satellite. So this is a small satellite, not a CubeSat, so it's basically 2 units what we mark here. But there is a lot of different initiatives, as I mentioned, both on European side and the US, in terms of targeting this question, the pitch angle distribution of the dust. In the end, I want to invite everyone to the HAPA Solaris workshop in 2020, which will be in Bergen in Norway in June next year. And finally, references. This talk is based on 3 different papers, so I kind of merged them as they can relate to each other on the same topic. Okay. Thank you. Yeah.
With the anisotropy that's strong in energies, for these, we're talking mostly about trapped electron. And what, how much difference do you expect with the northern and southern hemispheres if there's different magnetic field strengths? Galvanic anomaly distributed more easily than at the north, and that's going to affect the anisotropy.
It's a good question. We have kind of limited ourselves to the northern hemisphere to in this superposed epoch analysis, so I cannot answer that directly. That's and in the when we estimate the pitch angle, it will be in the pitch the loss cone estimate as we all the time uses the magnetic field, so it should be in there, but I haven't looked at it. That's it will give you more precipitation as there's when you have the weaker magnetic field. But in terms of the anisotropy, I'm not sure how it would look. That's the same. Yeah. There is an updated version of the AP model that is for different magnetic local times, but I've only used the first version, which is does not take into account local time, as this is what is being put into WACM and into this model into comparison project. No, it's for different energy ranges. So the model gives you can basically use it for different energies. So we use these are our bins, but the model is a mathematical description, so then you can make it for as many energies you want. The AP model assumes can't find a word. Sorry. The AP model assumes exponential spectrum. So they, when we estimate, we use a p-chip. So it's an interpolation between but the AP model by the Finnish group use an exponential. So that may be a slight difference if we compared the energy deposition as well. So the first group, so we start looking at the larger than 700 and 50 kV, and then the first group is where you have the enhancement there. But the second group do not have the 2 times, so they will be, there will be no overlap of the storms in that sense, but it still have something in large and doubling, more than a doubling in the larger than 300. So that will also happen here, but the first criteria is how does it behave in the larger than 750 keV bin. So this will be kind of similar in the two, group 1 and group 2, if that answers your question. I'm not sure. Did it make sense? Okay. That's fine.
How much total energy is or power?
Yeah, I can't give you a number. We haven't used it that much to look at the hemispheric power in that sense, but there is a different. There is definitely more overall energy coming in compared to the trapped particles. But what makes it a little bit more interesting is that it's being deposited deeper into the atmosphere, so it has a shorter distance to travel to the upper stratosphere. So it provides a more direct impact. But I can't give you a number, sorry. It's
going all the way back to the beginning of your presentation, talking about chemistry of protein, so can you say something about analyze the range of energy? Ones that are most important, ones that are all important.
they are all important. If I should favor one, it's the overall particles. They are basically there all the time, if we're looking at single event, it's the solar protons that are more important. But if you look at on average, I think it's the overall precipitation, and I think we have a fairly good idea of how much energy is coming in with them. Not perfect, but fairly good. But the reason I'm focusing on this part is because it's unknown. It's still, we still, as I showed, we cannot be sure within an order of magnitude what is hitting the atmosphere. So it's so in that sense. But to your question, if we're talking about individual events, solar proton definitely gives the biggest imprint. On an average, I would say the overall particles will produce more NOx, and they are more like there all the time. And this is a little bit unknown. So we have had a few studies looking at which is most important between these two. And it seems like on rare occasion you can get an impact all the way to 50 kilometers. So you see NOx production all the way down, but that's not a common event. So so basically it will be the transport afterwards with the overall particles that will be important then for the stratosphere. Yeah, if I should favor one. That's, did it make sense? It's a bit of a hand waving, not numbers. It's,
This is what I've never understood about radiation precipitation. Why can't you see it?
Well, then it's overall physics. The visible aurora is above 90 kilometers. And I think deeper into the atmosphere there is a lot of these excitation. They get quenched, and I'm not sure, but you don't see it. Yeah, but still. Yeah. But I think they are weaker, and you see them if you look have your X-rays images on, because they will produce X-ray. So in terms of X-ray aurora, you would see it. Yeah, but I think in terms of the energy input, you don't get much direct heat from this precipitation because you're getting into a fairly dense atmosphere compared to the lower thermosphere. So it's, yeah, so we don't see direct heating from these particles. It's not enough. But yeah, I don't remember my oral physics well enough in terms of to say why we don't have visible aurora from 70 kilometers. Maybe we do. Maybe it's too weak. But X-rays we do. Yeah. Yeah, the Pixie instrument. Yeah. That's no, but it's you get a nice auroral oval from looking at the Pixie. So it's definitely auroral X-ray aurora. Yeah, it is detect ionization, and also balloon measurements measuring X-ray also is produced by the same particles. So they are there, but yeah, to what extent we still don't. We're not doing a good enough job quantifying it. We're on our way.